electrons or waves, what we're saying is that they have more electromagnetic energy, right? Because that's our term for what we're calling light, right? They have more electromagnetic energy property than they do mass, or not necessarily than they do mass, but depending on how you measure their properties, you can get them to behave as a wave or as a particle. And remember this video here that we have to the left, we talked about this double slit experiment, right? Where waves have specific properties that when placed through a double slit like this, then you would get a different pattern on the back wall, right? So we talked about that. Now, we want to have a little bit of review about in terms of the properties of waves, right? We talked about waves having different wavelengths. If we have a short wavelength, hold on just a second, Okay, so waves and properties. Different wavelengths, right? We talked about how wavelength, and this is this equation here, wavelength and frequency, the product of the wave's length and its frequency, how frequently it goes up and down, right, is the speed of electromagnetic energy, or the speed of light. Okay? So we should be able to, I'm sure there's going to be at least one question where you're given a wavelength, a specific wavelength, and you're asked to find the energy of that wavelength or the frequency of that wavelength, or you might be given the frequency and asked to find the energy. All right? So what we need to know is the relationship here between the speed of light and the wavelength and the frequency. Okay? Now, again, the way that you're going to memorize this isn't by putting it on your headboard and such. It's by using the units, because frequency will be in units of per seconds, how frequently it goes up and down, how many times it goes up and down per second. Wavelength will be in units of a length, like nanometers or meters. And the speed of light, which is a constant, will be provided for you in terms of meters per second. Or, yeah, and generally that's how it's given. Okay? So, wavelength corresponds to energy inversely, meaning the shorter the wavelength, like this UV light here, 320 nanometer light, the shorter the wavelength, the higher the energy. Because the speed of any photons of electromagnetic energy is the same. How frequently it goes up and down is going to be the determining factor in the energy of the wavelength. Okay? So, now, we've seen this before, where you have different colors of flames. Now, in a campfire, you see it when you put in newspaper or something like that. You see little sparks of green every once in a while. And what's happening is we're getting different elements, and those elements are being excited. Okay? Now, let's pause for a second and think about what it means to be excited. Okay? So, let me bring up this thing really quick here. Okay? So, when we say something is excited, a system is excited, we're talking about the electrons in the system. So, if I have a nucleus, let's choose an atom here. Let's say I have an iron atom. All right? If I have an atom of iron, how many protons in an atom of iron? Anybody know? 26. Very good. 26 protons in an atom of iron. No charge, therefore it means 26 electrons as well. Now, those electrons are in these layers, which we call orbitals. Okay? Not all 26 can reside in one single orbital. You have a stacking. And as you get more and more electrons, the orbital gets farther and farther away from the nucleus. Okay? So if this is what we call the outer electrons in this specific atom of iron, for example, when electromagnetic energy that can excite these electrons hits these electrons, they will be excited to a higher excited state, we call it, an excited state. And that new orbital, right, that new orbital has a different energy. Those electrons will go out there. And again, how did they get out there? Well, a photon of electromagnetic energy hit them and excited them, gave them more energy. All right? And you can think about this maybe having a ball on the end of a spring. And if you swing that spring around your head, the ball will get farther and farther away the harder you swing it, right? So if you add energy to it, then it gets farther and farther away. Okay, so you guys, unless you're going to ask a question, if you could put it on mute, that would be great so that everybody else can not have to listen to your background, okay?
Yeah. No worries.
Let me hold on just 1 second. Leata?
Yeah.
Can you put it on mute until you're ready to ask a question?
Sorry, I didn't realize.
No problem. If everybody could put it on mute until you're ready to ask a question, that would be great. And Manu Lua, if you want to, and Luis, and anybody who hasn't, Catherine, anybody who hasn't checked in with a microphone, if you want to log out or try to figure out how to get a microphone, you're going to need that to communicate with neighbors when I put you into groups. So you might want to be looking into how to get your microphone up and running. Okay, so back to this. A photon of energy hits an electron, and that gives it more energy, and so therefore it becomes excited, goes out to a higher energy level. Then, as that electron drops back down, the energy is released in the form of a photon of energy as well. Okay, and this is, if it's in between 400 and 700 nanometers of wavelength, right? Let's say this is 600 nanometers. That means what? What's special about that wavelength, 600 nanometers? In terms of our eyes, what's special about it? We can see it. That's right. We can see it. We can see it because we can see anything that's in between the range of 400 and 700 nanometers of light. Okay? Now, this idea here, or this phenomena, that the different elements gave off different colors was kind of confusing because the standard idea was that we have these electrons around an element, right? Let me kind of start over here. We have a nucleus, and we have these electrons around the element, all fine and dandy, right? And if electrons receive a photon of energy, then they're excited. That, nobody had any problems with that. That was consistent with the photoelectric effect as well, right? If you shine the right wavelength of energy, then the electron can be excited. But the thing that was hard to understand is why there's only one specific color. So why do you get elements that are specific to their types of colors? All right, because the red wavelength of energy, that's the 700 nanometer. The purple here, in the case of potassium, that's your 400 range. Why can't this electron, which is being raised to an excited state here, why can't it be raised to multiple excited states, any excited state that it wants? And if it would be able to be raised to any excited state that it wanted, then it would be able to release all colors of energy that it wanted. And if that was the case, what color would you get if you were mixing all colors of light together? What would the resulting color be? Anybody know?
No.
What happens when I mix red, orange, yellow, green, blue, all the colors of light together? What happens? What color do I get? White. That's right. I get white color. What we know as white light. So when we see white light, that's really a mixture of lots of different colors combined. Okay. So why wouldn't all these elements result in a white color? when they're burning, because there would be seemingly an infinite number of distances that this electron could reside from the nucleus, right? An infinite number of distances. It could be, let's give some values here just for fun. 1, let's say it's 1, I don't know, we don't want to give it these are in, picometer, really small stuff. But let's say it's 1. It could also be 1.001 or 1.000001, right? So this was the rationale. If we have a nucleus here with an electron going around, why can't it be infinite number of distances away? And what that showed was that because these elements are all giving off different colors, there's fixed distances at which those electrons can reside. So you have a nucleus here, and depending on the kind of nucleus it is, it determines how far the outer electron can jump and also relax back down. So the color of the wavelength that's going to be released when that electron relaxes back down. Okay? So the different colors that elements give off when they're excited is an indication that electron location in the atom is what we call quantized. Quantized, like you quantify it, it's quantifiable. It's not continuous. It can't reside in absolutely any distance from the nucleus. It has to reside either here or here. Now this was bothersome as well, because if I think about like maybe a tennis ball being that far away from my nucleus, and I want to move it to be out here, well, if you had to move it from here to there, then it had to have been in all these different spaces along the way, right? So if it behaves like a piece of matter, it would have to reside here and then reside here. It would have to move out there. And so these were, again, along with the double slit experiment and other phenomena, it was indicating that the particle the electron isn't behaving like a particle. It's not a particle, it's a wave. We can measure it as a particle when our device kind of lends it to that. But other than that, everything was indicating that this is a wave. Okay? So, let me show you this. Well, here's another thing here. If you put an element within a tube, a glass tube, a vacuum, and then you apply a voltage to that tube, and this is basically what light bulbs are nowadays, right? Like the light bulbs above us on, long, thin light bulbs, and even the windy ones nowadays, they are just tubes full of gas in which there's a little bit of a vacuum on those tubes. That's why they pop when you break them. And then a voltage that's applied sends electrons through that gas, excites those elements, and we choose to put in elements like mercury, which are going to give us a nice white color, because that's the color we want. Some people choose different colors. Like if you want a sign that says open, you might want it to be red or blue, so you choose neon and put neon inside the tube. And that's what we call neon lights, right? So depending on the element that you put in, you get a certain color. On the big island of Hawaii, they're concerned about light pollution for the telescopes. Has anybody been to the big island before and seen what color the street lamps are? Anybody seen the street lamps on the big island? What color are they? They're this color. They're made of sodium, and they give off the color of this sodium flame here, this bright yellow. Or not bright, but deep yellow, right? So, depending on the color of depending on the element within the tube, the color that results, a different color will result. And if you pass that light that is emitted by that different element into a prism and break it up into its different components, then you'll get a very fingerprint-like expression or indication of what your element was. And so you can use this pattern of the different components that are making up the wavelength or the emission spectra of this light. You can use that pattern to identify what that light is and learn more about it. This is how they can look into telescopes at galaxies millions of years away, light years away, right? And see what elements they're made of, right? So that's how we do that sort of thing. So let's talk about the word quantized. The word quantized, kind of the opposite of quantized would be continuous. And the continuous idea is that you have a tennis ball, and that as it moves to here, it's going to kind of reside in every single possible location as it's moved from one spot to the other. Like this turtle could be continuously moving at small, different increments down this slide. It could be in absolutely any location from this spot to this spot in terms of height, right? Now, if it's a quantized system, the turtle can only reside at this level, or this one, right? So electrons are not continuous in terms of their distance from the nucleus, and distance from the nucleus also corresponds to energy, the energy that the electron has. The closer the electron is to the nucleus, the lower its energy level is, because it's receiving more of that positive charge interaction, and so it's stabilized. As an electron gets farther and farther from the nucleus, kind of like the analogy of the bonds, right? So if I have a bond that exists between these two nuclei, and we draw it as a spring, if I have that bond that exists between these two nuclei here, if that bond is high in energy, then the distance is relatively large and it's easy to break. Same thing with a nucleus and given electrons around that nucleus. Electrons that are far away here, those electrons that are far away are higher in energy, meaning they could be stabilized a lot better than they currently are being stabilized. And so that's how chemistry occurs sometimes. You have a nucleus here that is poor in electron density. This one is relatively high in energy and can be stabilized by transferring to a different atom, right? So, electron energy corresponds to the distance it is from the nucleus. All right, so quantized musical tones. What do you think? Let's see. I'm going to try to put you into little groups. All right. So you're going to be in these groups, and we're going to see if you can talk to your neighbor. Whoops. Let's see. How many people do we have? Okay. So it looks like we have about 4 people a group. So talk to your neighbors, talk to your groups, and see if you can answer this question. Which for the following provides quantized musical tones? Okay, I'm going to give you about a little less than a minute. Go. Did you guys talk about it already? Joey, Quincy, are you guys there? Jacob?
We're there now. So, which of the following provides quantized musical tones? What do you think? Yeah, 1 second. Okay. Okay, what do you think has quantized musical tones? The joy of doing this with roommates, right?
No, it's all
Okay.
good.
Okay. So quantized is like when he was talking about is the different like it only can go to different sections, right?
Yeah, I think so.
Okay.
Values are allowed. Yeah, it says energy is quantized if only certain discrete values are allowed.
Okay.
So,
I'm trying to think of like I don't know because it's kind of.
I don't know. At first, I was thinking piano, but I feel like it could hit like every note.
Yeah.
There's so many keys, and so that's probably not the right answer.
Would you because like you would think about a violin and a guitar too, like those seem so like fluid, you know, when they're. A flute.
Like it wasn't like they didn't fill out like in the boxes like they didn't sign anything.
Hello?
Hello?
Okay. Is everybody back? Is everybody back? Alyssa, are you there? Ashley? Riel?
I'm here.
Okay. Emily Eddington, are you there?
I heard a key.
Okay, great. So hopefully we're all back. What do you guys think? Which one provides quantized musical tones?
I think piano.
Piano? Let's see.
Yeah, piano.
How about a human voice? Let's think about a human voice. I'll give you my interpretation of quantized musical tones. Ooh, ooh. Am I singing in
Okay, I'm kind of thinking flute now.
Was I singing in quantized or continuous tones? If I go continuous, right? And the human voice can hit all sorts of notes. Have you ever thought about that? Why does the piano come in discrete tones? There's definitely noises that can be made between, for example, a B and a B flat, right? We can make noises between those two, but the piano only will play the B flat. It won't do a B half flat or whatever, right? However, violin, guitar. I don't know if you guys have ever been to the PCC and heard of the Hawaiian, what's it called? Hawaiian steel guitar, where it slides,
Black key.
wow, 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 right? It slides as it arrives to the note that it wants to play. And a flute. A flute also has the ability to kind of tune it and change the tones there as well. All right, does that make sense? Any questions on that?
So like, what's the answer?
The answer is a piano. A piano. The piano can't play sounds between a B and a B flat, right? You're limited to a number of notes, not just 8 in the octave, but you have flats and sharps. But that's it, right? Whereas in reality, there's an infinite number of tones, sounds that can be made between any two of those given notes. Okay, any other questions on that? How did your breakout session go as far as feedback for that? Anybody want to say, did anybody not be able to talk in their breakout session? Does that mean everybody got to talk with somebody else in their breakout session?
It was all good. Just when I came back, I had to log out of the. It wouldn't work when I came back into the big normal.
Okay.
classroom.
Did anybody else have?
That happened to me too. I couldn't hear you when I came back, so I had to log off and log back on.
Okay.
Yeah, that happened to me too.
Yeah, me too.
All
You
right.
should just
Say that again.
I just said there's going the audio again.
Okay. Well, hopefully we can get used to that because I think that that's a valuable tool. We need to make sure we're all paying attention. We're all interacting with each other. That'll help us learn from each other as well. Okay? So yeah, again, when you come in next time, try to come in logging in with your microphone. If you can't figure that out, that's a good homework assignment for you. Figure out how to log in with a microphone. Okay? All right. So, quantized. Orbits of electrons are quantized, and we call them orbitals. Let's see here. We got to. This needs to be restarted for some reason. So orbitals for electrons are quantized. That means that electrons can reside at specific energy levels, which is identified by us as distances from the nucleus, but it can't reside at infinite different distances. There's only fixed distances that it can reside, and therefore it's also what we call fixed energies. There's fixed energies that electrons can have, and we want to kind of have a way to account for these energies, give these energies what we call quantum numbers. And so the first quantum number that we're going to kind of talk about is our n quantum number, n equals 1, where n means the orbital number or distance from the nucleus, okay? So if I'm having a little bit of trouble with if I draw a little nucleus here, right, and then I try to draw orbitals around it, okay? And this is kind of why our initial model, right, our model that we were always using is drawn this way, because there really are fixed distances in which the electron can reside around the nucleus, right? The electron can be here, here, or here, but in terms of location, if we want to treat it as a particle, it can't reside in between any of those two spots. So that distance is defined as n equals 1. So let me draw a text box here. N equals 1, whoops, lowercase n. All right. So there's our n equals 1. This would be n equals 2. And you get the picture. N can equal any value, really, because you can get an electron to be excited. So if this was just a hydrogen atom, there'd only be one proton in the nucleus. How many electrons would there be if this was the hydrogen atom?
1.
Yeah, just one electron, right? And so that electron would be as close as it could be, which would be n equal 1 to the nucleus to start off with. But you could excite it. You could excite it to n equals 2, and then when it came back down...
I can't hear you.
You can't hear me?
Same.
Can anybody hear me?
Same.
Can you hear me now?
I can't hear you either.
I can't hear you either.
Yeah, I can't hear.
Okay.
Same.
I just refreshed
Same.
the page and it works for me now.
You can
But
hear me?
That happened to me too.
You can hear me now, Joey?
You are now muted. You are now unmuted.
Can anybody hear me now?
Just
You are now
refresh the
muted.
page.
You are now unmuted.
Can anybody hear me now?
You hear everyone else, but don't just.
Can anybody hear me now? 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 Hello, 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 hello. Hello?
Hello? Hello?
Can anybody hear me now?
Yeah.
Yes.
Yeah.
Yes.
Yeah.
Yeah.
Yes.
Yes.
Okay.
Hmm.
Still okay?
Oh, there you go.
Everybody hear
Oh,
me
there
now?
you go.
Now I can hear you.
Now I can hear you.
So,
Yes.
Yeah.
Yes.
the distance that the electron resides from the nucleus will be represented by an n value, where n will equal 1 for the closest orbital, n will equal 2 for the next closest, and so forth. And if we're talking about a hydrogen atom, there's one electron. It's going to be in n equals 1, but the electron can be excited in terms of energy and move to n equals 2 or n equals 3 or whatever n value you want to have. So n never equals 0. We don't ever have n 0. N is representing the distance from the nucleus, so there's always 1. And it's not in meters or nanometers or anything like that. It's in terms of energy. Okay? So that n value is a number that tells us how much energy it is, because it also relates to the distance the nucleus is from the orbital. Now, let's see here. Let me show you this YouTube video here of what we call a standing wave, because an electron is a wave, yeah, but it's not a wave like we kind of think of in terms of like an ocean wave traveling along the waters, right? It is what we call a standing wave, all right? And this little mechanism here is a string tied to a stick, and this is an oscillator. It just bounces up and down. And when it bounces up and down, you can see it moves the string like that. And so we're essentially sending energy between this pole and this string. And you can see that as the string speeds up, you get this wave. And maybe you've done this before with like a jump rope. where you can swing a jump rope faster and faster and faster, and you get these different ways that the wave modulates. Okay, so if I swing the wave the slowest, then I get kind of just a one half of a wavelength like that there. See that there? But as I speed the wave up, then I can get more what we call kind of nodes. A node is a region where there's no movement. All right? So if we get it even faster, so here is it in slow motion. You can see the wave moving. If we get it even faster, we can get multiple nodes in our standing wave. So there's one wave, or one half of a wavelength, right? And then let's see where we get to multiple nodes here. There's three right there. You see that? Three different halves of a wavelength, and two, and you can even count this, 3 and 4 as nodes, region where there's no movement. But this is the type of a wave that we're talking about when we're talking about an electron. We're talking about a standing wave. Now this is a kind of like maybe a one-dimensional standing wave. An electron is not a one-dimensional electromagnetic wave. It is a so here we have multiple nodes there now with higher and higher in energy, right? And so you could think of this as being maybe at n equals 1, 2, 3, 4, 5, where at higher energy and you get more nodes involved. All right. So it's this kind of wave that we're talking about when we talk about electron behaving like a wave. Okay, so a little bit of review here. We have different orbitals in which electrons can reside. They are quantized, meaning an electron doesn't reside in regions in between these orbitals, right? Again, we're also seeing how our model is kind of falling apart, because this isn't what the electron looks like. It's not a nucleus with these different distinct locations where an electron can reside. These locations actually represent different energies, the amount of energy that the electron has, and we're going to provide the n value 1, 2, 3, 4, and so forth that will relate to the energy and also the distance. Okay, when light is absorbed by electrons, what happens to the electron when it absorbs light? What do you think? What happens to an electron when it absorbs light? Alyssa?
It moves up an energy level.
That's right.
Or like an orbital.
And when the electron moves down, what word could we use to say what it does in terms of energy when the electron moves down?
Does it lose electrons?
Does it
loses energy,
electrons?
right? And it emits that energy. Emits that energy in the form of what? What are we going to see? Aisha, are you there? What are we going to see?
I don't know.
I don't know.
I didn't want to bother Kayla.
I didn't
We're
want
going
to
to see
bother
light.
Kayla, so.
We're going to see light. When electron falls down to a lower orbital, electromagnetic energy is going to be emitted in the form of light.
Will it be like a brighter light?
Will it be like a brighter
It's
light?
just
Or
what light is. The reason why we see light is because of electrons falling down to a different orbital. Now, in terms of if an electron falls, see this little arrow here. If an electron falls from this is n equals 4, right, to n equals 3, the distance that it falls will also relate to the amount of energy that is released. So, let's see if we can put that all together in our heads. If there's a transition between n equals 4 to n equals 3, all right, and there's also a transition from n equals 4 to n equals 2, which of those transitions will release a photon with the shorter amount of energy, shorter wavelength, the shorter wavelength.
I forgot to hit math.
Right
Okay,
now?
put yourself on mute.
Yes.
You can. Okay, so I'm gonna type that into here. If there is a transition between n equals 4 to n equals 3, and there is another transition from n equals 4 to n equals 2, which of these transitions will release the photon with, yes?
First, the third line is
Okay,
not
just a second.
displayed on the screen.
Shortest wavelength. Okay, does that make sense? We have two transitions, and we know that when the electron drops down, transition going from 4 to 3, and then another transition going from 4 to 2. Okay? Which of these transitions will release the photon with the shortest wavelength? Okay? So, whoops, we're going to try this again. I'm going to try to put you into little groups, okay? And we're going to take, hopefully, less than 2 minutes and talk about this. Is that okay? Okay. So, go to your groups and see if you can talk about it.
Is anyone else in here?
Is
anyone else in here?
Zafnath,
Okay.
are you here? You have to make it so that you can talk, so that you can contribute to the group. What do you think, Camille?
Well, I would think that it would be the N4 to N2 would have a wider wavelength. I mean, the shortest
Why is that?
wavelength. Would it be because like there's more light, like it's emitting more light?
Okay. Well, what has more energy? What's that?
N4.
The N equals 4.
The
Yeah.
N
Which
equals 4.
transition releases more energy? The N equals 4 to 3 or N equals 4 to 2?
N equals 4 to 2.
That's right.
N
that
equals
one
4 to
releases
2.
More energy. So would that one be shorter or longer in wavelength? If it
It'd be longer.
Oh, it'd be longer. So the first one would be shorter,
okay.
4 to
Let's
3.
think about that some more. What relates to the energy of a photon of light? Is it the wave's length? I mean, is it the shorter the wavelength, the lower the energy?
Wouldn't it be the
That's
longer,
right.
the lower the
Longer
energy?
the wavelength, the shorter the energy. Longer the wavelength, the shorter the energy. Or sorry, the longer the wavelength, the lower the energy. Right? The lower the energy. So.
I think your microphone just cut out.
Oh, that's what's going on here. Is it there now? Hello, 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 hello,
Hello?
Okay, are we all coming back now?
Yeah. Okay, you can do this.
Are we all back now?
Yes, I'm back.
We're back.
Okay, good.
We're back.
So then, what did you guys decide? Which of these transition will release a photon with the shortest wavelength? A or B? You can't hear us?
I can't hear you.
Can anybody hear me?
I can hear you.
I
I can hear you.
Excellent.
I can hear you.
I can hear you.
Okay, wonderful.
I can hear you.
I can hear you.
Yes.
If there's a transition A, this is our transition that's described in A, 4 to 3, and another transition B, 4 to 2, which of these transitions will release the photon with the shortest wavelength? What did you guys decide? A or B?
B.
I think
B.
it's A.
B.
I think
B.
A.
A.
We
talked about A, but it feels like
that's
the obvious one, so I feel like it's wrong.
B is the answer. B is the answer in terms of the shortest wavelength. What if we had asked this question, which transition will release the photon with the not shortest wavelength, but what if we asked the highest energy?
Wouldn't that also be B? Wouldn't that also be B?
Yeah, I think
it was.
Like the shorter the wavelength, the more energy.
Like the shorter the wavelength, the
so.
more
I
energy
think this
as
one
well.
is easier for us to think about. Higher energy, right? N going from 4 to 2 would release more energy than N just going 4 to 3, right? Is that a little more straightforward understanding? So that's easy to think about. But when they put in the twist, try to look at the shortest wavelength. Sometimes when we hear the word shortest, we want to think, oh, short wavelength, that means that it's low in energy. But it's the other way around, right? Because light, here's our two wavelengths of light, 2 photons, red and ultraviolet. They travel at the same speed, but it's how frequently they go up and down, which is related to their wavelength. So the shorter the wavelength, the higher the energy. All right, does everybody follow that?
So even though B is like a longer distance, it just matters of the frequency of the waves because it'll be like shorter.
Yeah, it's just going up and down
Wavelengths.
or less frequently, right? It's traveling at the same speed. If I understand what you're saying, when you
Yeah.
so
Yeah.
when we have a transition, we're talking about the transition from energy level 4 all the way down to energy level 2, right? Comparing that to 4 transitioning
Yep.
down to 3. When we have a transition that goes from 4 to 2,
Mm-hmm.
it's the electron is falling farther, and so more energy is going to be released. And when more energy is released, then the wavelength of light, the photon of energy that's released, is going to be higher in energy, and therefore going to have a shorter wavelength.
Okay, that makes sense.
Okay, that makes sense.
Higher is shorter, and then
So higher is shorter, and then lower.
Lower energy.
Longer.
That's right. So here's another.
lower energy, longer wavelength.
That's
Yeah,
right.
lower energy, longer wavelength, higher energy, shorter
And
wavelength.
so we had to make sure that we would see that the B here, which is higher in energy, would have to have a shorter wavelength, right? Okay, any other questions? Okay, hopefully we are able to do those breakout rooms. I need to make sure everybody has the ability to have their microphone working so that they can contribute to the breakout room, all right? So that's your job. Next time when I come in, I want everybody's little symbol on the left to show that they have a microphone and that they can communicate with neighbors as necessary to talk about questions. Okay? I'll see you guys on Friday at 11. True? I'll hang around to answer any questions about I'll hang around to answer any questions about the exam or anything like that. In general, our next exam, if you didn't get to take this exam, then the next exam will take the place of that previous exam. I'll try to work on getting an exam out soon, but we kind of need to have a little bit. Well, I don't know. I'd like to have a little bit new stuff on the exam, and we haven't quite gotten through chapter 8 yet. So maybe at the end of chapter 8, we'll try to have another exam. Hopefully, but that might be the final exam. I don't know how fast we can move through this stuff. So we'll see how fast we can move. Did anybody have any specific questions about anything?
Yeah, I have a question.
Yeah.
Yeah, I have a question. So our syllabus said that we would have the 3 exams and then the final. But are you adding another exam?
The more exams we have, the increased likelihood that you'll do better, right? So they're just kind of like practice. But we don't need to. We can just go right to the final. But I'm just trying to prepare you guys the best we can.
Makes sense. Thank you.
Do you know how we're gonna
Thank you.
Be taking exams? Is it just gonna be on
Yeah,
Canvas?
it's just going to be on Canvas somehow. I mean, we're still in the mix with the American Chemical Society to see if we can provide an online final experience that would be kind of controlled, regulated in such a way that it would be kind of like basically the online version of the ACS exam. Otherwise, it's just going to be kind of like the homework has been, right now at least.
What was the average score of the?
What was the
It
average
was
score
60%,
of the
which is
exam?
not bad, but there were people who performed poorer, and I think that most of that probably had to do with the different craziness that's going on in their life right now. So I'm hoping that things can settle down and we can get better at managing the new system, the new normal for a while at least, and then we'll see if we can do better on the next exam. Any other questions?
I have a question about wavelengths.
I have a question about wavelengths that we were just talking about. So are we referring to them covering the same amount of distance, and that's why the wavelengths are either like higher or lower than the other one?
When you
That
say
made any
covering
sense?
the same amount of distance, what do you mean?
Like your picture that you have right there of
The red and ultraviolet?
like the ultraviolet one is steeper, or not necessarily steeper, but narrower, and so there's more wavelengths. Do they end up covering the same amount of distance, and that's how we know that one of them is emitting more energy because there's more like peaks in that same amount of distance?
That's kind of one way to think about it. I lost my drawing software,
Okay.
so I can't draw. But when I come to class next time, I'll have that drawing software available. Let's see. What can I do?
Okay.
Look at this real quick. Let's just look at this real quick. If I can figure this out.
No, you don't.
Okay, so here's, I don't know if this will answer the question, but here is 2 photons of energy, right? The 2 photons of energy, one has, it's not a very good drawing there, one has a longer wavelength than the other, right? One has a longer wavelength than the other. They travel at the same speed, right? They both travel at the speed of light. So if they had they're racing from left to right here, they travel at the speed of light. They both have the same speed, but this one, I think this is what you're referring to in terms of the amount of distance it's covering. Like this sort of a wavelength photon would have covered a lot more distance in the amount of time it traveled from there to there. Is that what you're talking about, Joey?
I
guess I was saying distance rather than speed, just like the two lines that you drew on the side of them. I was referring to that as like they're starting at the same point and ending at the same point. but one of them is like more narrow or has more peaks than the other one.
For this particle or this entity, this photon, to get from here to there, compared to this one getting from here to there, this one's going to be doing a lot more moving.
Mm-hmm.
A lot more energy.
Right. Okay. Yeah.
Okay. Any other questions about anything?
Me and Alyssa were curious about the lab report. I know, like, we just have a question because there's some of the math on it that's difficult.
Is that lab report 4?
Yeah.
Okay. Did you get to watch that video yet online?
Yes. Alyssa, what was the? Are you?
Alyssa's still here. Are you there, Alyssa?
Yeah.
Okay.
She has the. Yeah. She has the notebook with all our stuff in it. She has the notebook with all our stuff in it. She has the notebook with all our stuff in it with specific questions. Just because it was, I know yesterday was Tuesday, but we wanted to wait today to
ask. Do you guys want to meet up in a different conference?
Can you hear me now?
Yeah.
Can you hear me now?
Yeah.
Sorry, it like shut off. Okay. So I have a question about how to find the concentration and weight percentage. I found figure out the weight in grams, but I don't know how to find the percent.
Okay. So once you find the weight in grams, can you hear me still?
Yes, I can hear you.
So once you find
yes, I can hear you.
You've identified the moles of, let's say, sodium carbonate, for example. Then you can convert that to grams of sodium carbonate.
Yes.
And then the grams of sodium carbonate will be divided by the total mass of the sample, which was probably close to 0.2 grams.
Okay. Okay.
Times 100.
Okay.
That'll be your percentage.
That's okay. I get it now. I just didn't know what we were dividing it by. It was late last night when I was trying to figure it out. Thank you.
There's 3 different components.
Thank you.
You have the sodium carbonate, the sodium bicarbonate, and then the remaining mass will be the sodium chloride.
And there's no graphs in this lab report. And there's no
graphs
in this
really
lab
needed.
report,
Just
correct?
you could put a table if you wanted to, but with all your different resulting volumes for the different sets of titrations, that would be okay, but not necessary either.
Okay.
Okay.
That's awesome. Thank you.
All right.
That's
Any
awesome.
questions
Thank
from
you.
anybody?
Could I ask another question?
Sure.
Oh, sorry.
Could I ask another question? Oh, sorry. You can go first.
It's just quick. I was just wondering about what are we going to do about the labs?
I don't know yet. I'm trying to get a couple of different things and try them out. The worst case scenario, I have about 1/4 of the students who haven't taken Lab 4. So the worst case scenario would be that you don't get to take Lab 4 and you just have a final experience that's online. If I can find some good software, there's some stuff out there in terms of titrations, kind of like online titrations, which, this is the best you got for the circumstances. Then we might have a Lab 4 from that sort of thing. But the lab final itself is obviously going to have to be some sort of an online, more like just an exam that's associated with the principles in lab and specifics of the lab reports that we've turned in. So I'm not positive exactly where we're at for that.
Okay, thanks.
Yep.
Okay, thanks.
Joey, you still have a question?
Yes.
Yes. I couldn't hear you during the part where you were explaining the answer to the quantized musical tone. So could you go over that really quick again?
Use my voice. You didn't
Thank
hear
you.
my good singing then, huh?
I guess not. Shucks.
Maybe
I
nobody
guess
heard it.
not. Shucks.
But if I can sing, right? People can sing, and I can sing. My voice can go, and I've hit every single imaginable tone between whatever note I started from and whatever note I ended by gradually raising my voice, right? And certain instruments can do that sort of thing. A violin, a guitar, horns. Well, I don't know. Can horns do that? Some horns can. Like an American in Paris. I don't know if that's the trumpet right at the beginning. I'm not terribly familiar with a lot of different instruments. But the piano is like a harp sort of thing. It doesn't really have the ability to make noises between, for example, B and B flat. It can do B and B flat, but it can't get the notes in between there, right? It can't get, well, there's no notes in between there, we say, because that's what we were raised with. There's only 8 notes, and some have flats and sharps, but that's it. That's all there is. But that's not true, obviously. There's plenty of different sounds, and you go from culture to culture, and people have identified the notes that they would like to have within their songs and stuff. But so a piano is quantized because it can play the notes that we're familiar with, but that's not all the sounds that actually exist. So that's what we're kind of thinking of in terms of a quanta, or why a piano is quantized. Does that make sense?
Yes, thank you.
Yes, thank you.
All right. Anything else for anybody?
Dr. Scott,
Yeah.
sorry I couldn't get.
Dr. Scott, I'm sorry I couldn't get. I couldn't hear when you were answering the part about the quantum number transition, about which one had the higher energy.
So, if there is a transition between N4 to N3, and we compare that to another transition, N4 to N2, all right? Hopefully, what comes to our mind is the nucleus, right? Let's get to this, whoops, let's get to this little picture here. A nucleus, orbitals, given different n values, right? And we have this transition, 4 going to 3, or 4 going to 2. And I think that we would probably pretty easily say, oh, 4 going to 2 is going to release more energy because it's fallen further, right? 4 going to 3 releases energy, right? But it releases less energy. So those two different photons, right, or if you could think of it as the color of those two different lights, are going to be different. Those photons of energy are going to be different. The one that's releasing energy from 4 to 2 is going to be releasing higher energy than the 4 to 3. And so then in terms of energy, maybe it's easy to think, oh yeah, 4 to 2 is more than 4 to 3, so highest energy release is going to be B. Now, in terms of wavelength, that's not directly relatable to us in our minds sometimes, because we might think, oh, short wavelength, that's short energy, right, or small energy. No. Shorter wavelength means higher energy because frequency relates directly to energy. And the shorter the wavelength, the higher the frequency. So that's why B is the answer for shortest wavelength as well, because the short wavelength has the highest energy. Does that make sense?
Yeah, it does. Thank you.
And the ICP,
Yeah, it does.
the instruments you guys use to do that work, you know, it knows the transitions that are allowable for a given element. So if this is an atom of tungsten, it knows that an atom of tungsten energized with that argon gas in that chamber will have electrons transitioning, not from N4 to N3, but it's going to be like N8 to N7, N7 to N6, and it's going to know the possible transitions, and because it knows those possible transitions, then it knows the color of the light that should be released. And so all it has to do is look for that specific color of light, that specific wavelength, and then it can use that to quantify the amount of tungsten that there was in the sample. And that's why sometimes there are transitions that can occur, because there's a lot of different kinds of transitions. You can see how you could get N4 to N3, N4 to N2, N4 to N1, N3 to 2, N3 to 1, N2 to 1, right? There's lots of different transitions that can occur. So sometimes two different kinds of elements, tungsten, cobalt, might have some wavelengths that are similar because of transitions that are similar in energy. Therefore, you have sometimes overlapping, right? Remember, we were looking for to identify which wavelengths didn't overlap, so that we could not have some mix-up between relating the color of the light to the concentration of tungsten or cobalt. Does that make sense?
Yeah, I remember this. Yeah.
Okay.
Yeah, I remember this. Yeah.
Thank you.
All right.
Thank you.
No problem. We'll see you guys on Friday if there's not any other questions. Okay. Bye-bye.